Good evening, colleagues. Warm welcome to Luxoft LTS Webinars. Before we start, a few words about our agenda for tonight and our speaker. In a few minutes, Odin will start his presentation. The speech will last approximately 1 hour, and then you will have a chance to interact with our guest. You can do it via Q&A chat. You now see on your screen where to choose Q&A box, and then you can post a question to our speaker. Odin will comment and answer after his presentation. And in case of many questions, you can find or meet Odin at different conferences or contact him via LinkedIn, for example. Also, if you want to know more about our latest news and events, please follow our pages on LinkedIn and Facebook. And now I will let Odin Holmes to introduce himself. One more time, thank you guys for joining us tonight. And now, Odin, your part starts.
Career about 20 years ago doing electronic engineering work. And as most electronic engineers, I ended up writing more software than I made circuits. Not for desktops, at least not mostly. I mostly write software for microcontrollers, tiny chips. And that's actually quite a bit different than a desktop, which has led me to create several libraries that work in this domain. I'm also a co-organizer of the EMBO conference, which is a bare metal embedded C++ conference here in Germany. Yeah, I'm going to talk to you guys today about statically checked interfaces. As I mentioned, statically checked interfaces are a more bulletproof interface that users can't break as easily or can't make mistakes as easily. As I mentioned, a minute, this is not working from a technical standpoint. There we go. As I mentioned, I'm a co-organizer of the EMBO conference, but now let's just jump in and see some code. If you look at this example, we can see some code that we've all seen in legacy code bases where the interfaces are very C-like. With lots of pointers where one could have used references and lots of native data types. And I don't know what your reactions are to this kind of code. It's probably quite mixed. My reaction these days is something more like this, or that's definitely going to break, or that's a huge can of worms. It's the mother of all cans of worms and has had babies. But by the end of this talk, I hope that you share the feeling that we need to fix this and build stronger interfaces that we can't break as easily. But what's the real problem here? Problem here is that we can't locally reason about things that are about correctness. In the first example, we take a pointer to int and we use it and assume that someone else has checked if it's a null pointer. If it can never be a null pointer and it also cannot change, we could use a reference. But since we are using a pointer and we're assuming it's not null, then that's probably for interface reasons because the pointer can change. It can change what it's pointing to. Now, the problem here is we are trusting other people across the entire code base, any possible caller, to check this pointer if it's null before they call us. And one could argue there probably should be a comment next to the function. We should probably say we're expecting a checked pointer to end. Problem there is that the compiler doesn't read comments and it can't check that for us. And if we're in code review and see the call site, see only where somebody's calling this function f, and we're passing it a pointer, we don't know in code review without looking at the other end, at the comment or at the body of the function or doing a relatively large code review, whether we're expected to have checked this pointer for being null or not. And there are examples of code bases where something like 30% of the code is just checking pointers if they're null or not, and handling the results where they're checked at every step of the way. And that's not only a lot of work, it's also still somewhat error prone, because there could still be the one spot where you didn't check, right? I mean, even if you have 1,000 checks in your code base or 10,000 checks in your code base, there still could be one that you missed. And it's not particularly performant, because you're checking something against null probably way more times than you really need to. If we set boundaries or arenas or interfaces where we expect things to have already been checked, then after that we no longer need to check. And with this second function, the received handler, the last two parameters are a size and a pointer to an array of char. That probably should be a vector in modern code, or some kind of range or array view or whatnot, depending on the semantics. We don't really know the semantics from looking at the code. I mean, are we expected to delete data? Are we, if this is very, very old code, we may be expected not to change data even though it's not const, right? So there's missing semantics in this interface. And there's also a somewhat more subtle problem here. I can switch around packet ID and protocol ID, right? With Qt interfaces or graphics interfaces, this happens a lot. You have a point on the screen where the start of a box is, and then you have an X and a Y, and then you have a width and a height. And if all of those are ints, then you can easily swap them around and get it wrong. And in this particular case of received handler, this is a bug that I actually had in my own code, my screw up, if you will. I did switch around packet ID and protocol ID on the receiving end of a network driver, a network driver for the CAN bus in the automotive field. So not the network that you're used to. But the amazing thing was that it actually worked, because packet ID 2 happened to be the handler whose receiver had this error, and protocol ID 2. And protocol ID 2 was a protocol which opened a channel so that we could communicate on other protocols with different nodes on the network. And so there was only ever one answer and one sent packet in this protocol. So we sent it out, that was packet ID 1, and we received a packet, that was packet ID 2. And after that, we communicated on a different protocol through this tunnel. So it actually worked, even though I had switched them around. And it worked in the field for weeks before somebody with a car that was only manufactured in China, I believe, had a control unit that took longer to answer. And so it would send a hold on a minute, and then, okay, the channel's open, right? So a wait and then an acknowledge. And so then there actually was a packet ID 3 on protocol ID 2, and then everything crashed, right? So this was a really, really, really hard bug to find, because I couldn't actually test on hardware. Like, I'm in Germany and the car's in China. And this took me probably, 2.5 weeks of my life trying to figure out. And but before that, I was kind of in the camp of, let's type less and we'll get it right anyway, and we'll just look at it and be careful, and let's not write more code to make sure that our code is correct. And after this bug, I realized I could have typed a lot of code in 2.5 weeks. Like if you don't have to think about it and you just type code all day, you could do, I don't know, 20,000 lines or 50,000 lines of code or something. A large portion of our project. I mean, most of our time we spend thinking or debugging or code reviewing or talking to other people about how to use our interfaces. And it actually saves time if you invest a bit of time in teaching the compiler how to enforce your interface semantics. Remember the comment on we're expecting this pointer to be checked. Well, why can't we codify that comment? And if we think about how to do this, the compiler already has a built-in mechanism where it's checking things for us. I mean, we see this every day, so we may not think of it in that way. But if you think about the int pointer, well, the compiler knows that I can dereference an int pointer. The compiler knows I can add an int value to an int pointer, and then we'll point to something else. The compiler knows that I can't add 2 int pointers together. I can dereference them and add their values, but I can't add 2 pointers together. These are rules that come along with the pointer wherever it goes, and there's rules about what it can be converted to in other types. And there's also there's rules about what because it in the underlying in the release build, in the actual binary, this type information is gone. This is these are just 4 or 8 bytes that get sent to our F, right? And whether it's a signed int or whether it's an int or whether it's something completely different entirely, we don't know in runtime if we don't include debug information, because the type information is just inside the compiler. And that has the advantage that if it's just inside the compiler, it doesn't cost us anything at runtime. So we can try and leverage this type information in order to add rules to this to our interfaces. I mean, we could, for example, add const to an interface that's provided for free by the compiler, and that sticks along with that type. We can add const, we can't remove it without a cast anyway. So if we think about things on this level of, there's essentially a trilogy which everything else builds on. I mean, the only thing that we really have from a theoretical standpoint that we're really dealing with is data, which is just raw bits with no meaning without type information. There is type information, which is compiler internal. It's the only evidence of that the type information was even there that we see in the compiled binary is the choice of what functions to call. And I wrote subroutines here, which is a more generalized function. Operators, for example, are subroutines. They may not be considered as functions, or I don't know, exception handlers or things like that are not something we'd think about as a function itself, but they are subroutines. And so which function or which subroutine is called on a piece of data depends on the type information, right? If I print an int to the screen, it's probably going to show me a number. If I print a unsigned int, a uint8t, as in an 8-bit int to the screen, it's still going to show me a number. If I print a character to the screen, it's going to show me a letter. That means a different function got called, even though the data in both cases was just 8 bits. A different function got called when printing to the screen. And we're familiar with this from function overloading, but this is basically what the world's built on. So let's try and leverage this information. The way I solved the packet ID protocol ID, or the way I made sure that there weren't any other problems was actually quite simple and quite pragmatic, if you will. It's not a very elegant solution, but this is where it starts. If I create a struct with a member, then this struct with this member, if you think about it in data, it's just an int. It's just 4 or 8 bits, or maybe even just 2 bits, depending on what platform you're on. It's not costing us anything at runtime, but it has extra type information. By calling the constructor explicit, we tell the compiler that it shouldn't implicitly cast an int to this data structure. So we actually have to explicitly say, you see in the second to last line, we're explicitly saying protocol ID number 2, right? We can't just put a 2 in. That will be a compile time error because 2 is not convertible to this struct that we just created. So if we want to convert from int to a protocol ID, then we have to explicitly call the constructor. If we want to convert back from int, from protocol ID back to int, then we can just access the member variable. This is, as I said, not very elegant. C++ has conversion operators. We have many more things that we could add to this class to make it look more seamless. But the point I'm trying to make here is this is a pragmatic choice that I made for that particular code base, where it is a little bit ugly, but at the same time it's much safer, and it's not a lot of hard work, and it's not a lot of complicated C++. We are going to see a lot of very complicated C++ towards the end, but you can start very, very small. So from a performance standpoint, we're not changing anything. I mean, in debug mode, the constructor will run, but in release mode, the optimizer will see that we're converting number 2, which is an int, to basically the same bits, right? So no subroutines will run. It's just for the compiler to be able to reason about correctness. So if we typify our interface with a packet ID and a protocol ID, then it's already pretty bulletproof. Like, we can't screw this up in the same way that we could in the original interface. I also added the vector char. That means that this is owned. If the semantics were here, I'm giving you a pointer to a buffer that you don't own, as in you don't have to delete it. That's kind of the meaning of ownership in this context. Then I could have used an array view, or in newer C++ ranges, or if you're allowed to use boost, you can use boost ranges, or you can also pass a pair of iterators, because that's semantically a pair of iterators semantically means that you don't own the underlying data, whereas a size and a pointer is pretty ambiguous. So if we want to solve the other problem is a little harder, the checked pointer, because it's not just about switching values around. Oh, I see there's a question. Shouldn't vector be taken by ref or constref? That depends. That's actually a very interesting question, and it changes. The answer to that changes as of C++ 11, because before C++ 11, if we take a vector by value, then that will mean that a vector will need to be copied into our function in order to call it. Whereas after C++ 11, we have something called move semantics. And what move semantics mean in a nutshell is that if I'm not using something anymore, right? A vector is composed of two sets of data. There's the one set of data which is on the heap, the variable size buffer of the vector, and there's one portion of the vector which is on the stack, which is quite small. And the portion on the stack, well, I have to copy that. I can't move that anywhere because it's on the stack, right? It's in my local storage. But if I'm calling a function and it wants a vector, and I have a vector that I don't need anymore, then I can move my vector into this function rather than copying. And what that means under the hood is that the pointer that I have to the heap, I'm going to give up on that other vector, in which case I'm just copying a pointer rather than the entire contents of the vector. So passing by value in C++11, as long as people move things in the case that they don't need them anymore, is equally efficient as passing in a reference, but has the added advantage that I don't have to worry about keeping the thing that reference is pointing to or referencing alive for the duration of the function call and for the duration of any iterators that it may have stored somewhere else. I mean, this is somewhat a hard problem, but if I move into it, then it's no longer a hard problem. If the data is constant, as in it's not changing, then I could also pass in via constref. That would be also acceptable in old or new C++. But that's for the case where I'm not going to mutate the vector. In the case that I'm not going to mutate the vector, we also get new tools in newer versions of C++, like views, which are more generic. If I'm not changing it, I don't have to know how it grows, for example, right? So if I have a view rather than a reference, then I can also have views into other data structures and support them with the same semantics. So back to the pointer problem. With the check pointer, I need to add a little more semantic content, because with protocol ID and packet ID, it was just a question of not swapping them around, right? Whereas with the check pointer, I don't want the user just to be able to construct one of these things with a pointer, as we did with protocol ID. I want to, if they construct me with just a pointer, then I will check it, right? And this second template parameter is a user supplied checker, which will, I don't know, throw or do whatever the user wants to do if this is a null pointer, right? So that also will cost us runtime cost. So if we are taking the address of a variable that we already have in non-pointer form, or we just called new, although new should probably pass its pointer immediately on to some managing smart pointer, like a unique pointer or a shared pointer or something. So new's maybe a good example, maybe not. But if I'm taking a pointer to a local variable or to some global variable or something, then I know that that's not null. I'm taking its address, and so we want to give the user a way to express that, and that's why we're creating this tag called checked. And a tag is just a fancy way of saying an empty struct, or a type that we created solely to add semantic content to an interface, right? This checked struct is empty and has no meaning except for it's a way that we pass information to an interface. We also are using the option of being implicitly convertible to the underlying data type, which we could have used with packet ID and protocol ID. If you see that operator T, that's a conversion operator. So if we want to use this as a pointer, it will silently convert itself to a pointer for us. Because converting from a checked pointer to a pointer is not dangerous. The other way around, converting a pointer to a checked pointer is potentially dangerous if that pointer is null. So let's use this checked pointer. First, it could be a pointer to anything. If we look at this first line, we can templatize it on a pointer to int, and we can throw in whatever checker we want to write, and create an alias so that it's saves us typing, called checked int pointer. And if we take a checked int pointer in the interface of a function, we don't have to be afraid anymore that that pointer may not have been checked. We also don't have to write any comments or anything. It's completely clear in code review, or to you reading your own code later, or to other people reading your code, that it is expected that this pointer is checked. And this is even enforced by the compiler to a certain extent. If somebody just passes a pointer that has not been checked, then that will be a compile time error. They have to pass a checked pointer. And when you construct a checked pointer, if you look down a couple lines below, the variable CP, where we construct that, we're giving it the address of our local variable, so we know that's not null. So we can just drop in that tag checked. And at that point, we are not creating any runtime overhead again, right? Because the constructor is not doing anything. It's copying the same bits that we otherwise had. The compiler is also very good at eliding copies. Eliding is another just fancy word for not needing to do. Realizing it doesn't need to do and taking them back out. So under the hood, in the release version, all we are doing is sending, some number of bits, probably 4 or 8, that represent the address of I to the function A, right? The runtime will contain byte for byte the same code, whether we are dangerous and just pass an int pointer, or whether we are safe and pass a checked pointer. The last line, or the second to last line with the comment, we can see that this will be a compiler error because we are passing just a naked pointer to our checked pointer interface. And once one starts to add these kinds of things to the code base, this was actually the same project where I made the mistake with the packet ID and protocol ID. I realized at some point that I had a very large architectural error, if you will. I had built the entire program around an assumption of latency. And oh, sorry, I see another question. I'll answer these things as quickly as I can. Okay. Oh no, it was just reminding me that I forgot to press solved. Sorry, everyone. I'm getting used to this interface. So in this project, I had to refactor a lot of code because I had made an assumption about determinism and latency, which I could not fulfill, or which was wrong, and the real latency requirements could not be fulfilled with the strategy that I was using. And so I refactored a lot of code. Like I was typing for days without compiling, just refactoring. And usually that would be an absolute nightmare, right? Because you're breaking all sorts of stuff. But it was, to a certain extent, a thought experiment. I mean, I think the diff in JIT was 10,000 lines or something that I had touched. And when I did compile after all of that typing, I got 40, 50 compiler errors. And when I started to go through all of those 40, 50 compiler errors, they were all mostly stupid mistakes where I had, swapped things or giving the wrong value, or, the interface had changed and I was still using the old interface. And many of those would have been runtime errors if I hadn't checked my interfaces correctly. And this is probably luck, but after I had fixed all the compiler errors, then all the units tests passed, right? I had touched 10,000 lines of code and I hadn't broken anything. Well, I had broken 40 things, but the compiler told me. Okay, I'm seeing some new questions here. What's the benefit of check pointers versus passing a reference? That's a very good question. I mentioned at the beginning, but probably too long ago for it to be relevant here, that using a pointer that cannot be null essentially only has one use case, and that is if you want to be able to point to something else later, right? If I have a pointer to element 1 and I want in my function to be able to point to element 2, 3, 4, 5, 6, iterate through them or something, then I can't use a reference because references can't change. They can't be null and they can't change. Whereas a pointer can be null and can change. And in this case, we want never null but can change. And there is no built-in type in C++ which fulfills that, which is why we built our own. But it's an excellent question. Okay, other question. Idea of wrapping int or other primitives into a struct is good, but I personally resorted to just being more careful because doing such wrappings all the time is very tedious. How would you approach that? Well, yes, this is essentially exactly the opinion that I had before this project, and if it helps you any, in retrospect, I think I was wrong. But it really depends on your domain. Like, I don't write the same C++ code for the same targets with the same design requirements and so on and so forth as other people do. I do concede it is a lot more typing. You can get fancy with templates. There are a few libraries out there that mean that creating your own unique type is just one line of code, and then if you consequently implement this throughout your entire project, then a protocol ID will only change from int to protocol ID at the boundary, where somebody's calling your DLL or somebody's calling you from a C interface or something, and will continue to be a protocol ID throughout your entire project until at some point maybe it goes out the other end and turns into an int again. But in most cases, the names are longer, but that's probably good because the extra characters you're typing into the name are extra characters you don't have to type into a comment, right? If you have an int called protocol ID, well, what does that mean? I mean, protocol ID and packet ID are also things that could also be strongly typed enums. The new enums that we have in C++ 11. That would be another example that would work quite well, at least for protocol ID, because they don't change. Whereas with packet ID, you might want to do +1, and when you want to mutate the state, in any sort of scalar manner, as in add something to it or something, then enums break down as an opaque reference. But my point is, you do type more, but that typing saves you, in my opinion, more time debugging and communicating to others on the project how to use interfaces, because the interface becomes, you can't screw it up as easily, and so you don't have to communicate as much. It depends on the company. Many companies, their C++ developers spend more than a third of their time in meetings talking to each other about this kind of thing. And I think a lot of that could be saved if interfaces were a lot more, idiot-proof, if you will, right? Like, If I don't read the manual and start playing around with it, how dangerous is that? Well, that really depends on how well the static checking in that interface is. Okay, good questions in this session. Moving on, we can obviously pass a pointer that hasn't been checked. If you can see, the fourth to last line is changed where we're constructing CP. In that case, the checker will run and throw an exception or call terminate or whatever you want to do, log error, I don't know, depending on what checker you passed. We also don't have to construct one on the stack. We can also just do it on the fly in place in the call to A. Now, whether or not this is more efficient, you don't have to believe me. There's a wonderful tool for checking this kind of thing, made by Matt Godbolt. You can find it at godbolt.org. And in Godbolt, on the left pane, you can type in your C++, whatever it is that you want to check. And then on the right-hand pane, you can see the assembler that turns into. And you all can also select one of something like 40 compilers. You can also, set compiler flags and so on and so forth. And, here, you can see that we're in debug mode because there's plenty of assembler left, right? Like if we were to add next to that minus std equals C++14, the compiler flag of yes, we're using C++14. We were to add a minus 03, as in optimize, then that would obviously all go away because nobody's using I, so the compiler will just get rid of it. This is, you don't actually have to understand assembler very well in order to use Godbolt. That's kind of the magic of Godbolt. You put in your code, set it to release mode, and less assembler usually means faster. Or if you look for jump commands in assembler, those are something you probably should recognize. You can then recognize loops, for example, or loops being unrolled. If there are no jumps anymore, then it maybe unrolled the loop. It's actually probably quite easy to check the stuff that we've seen so far on Godbolt in release mode because the assembler will be identical in the vast majority of cases, unless we're actually checking to see if the pointer is null, in which case there will be more assembler. But if you wrote a checker yourself, as in you checked against 0, then it would probably be pretty equivalent again. But by adding the contract, this plays into the idea of contract-based programming. By adding the contract of an interface taking a never null pointer, we are saving a lot of checks behind that interface because that function may call another function and pass the pointer along. And if we establish a boundary where the pointer is checked, and then after that, propagating through using the type information to propagate from one function to the next, we could also even make like an overload of some trivial functions for I have a pointer or I have a check pointer, and this is not just good for pointers. I saw an example yesterday in a talk that happened to be a similar very, very similar content at the For Developers conference, where the example was being used with an SQL statement, where an SQL statement, some of them don't have injection or any kind of hacking problems because they come from within your program, right? Like if you're using your text string to query a database, then you don't have to check if somebody's putting a drop table in there or something, right? But if you're taking SQL from the user side, then you do have to check, right? And so, that's another example where, I mean, you could just be really careful and save yourself some typing and explain to all your colleagues how they have to be careful and write documentation about how future people in your company after you leave need to be careful. Or you can encode that into the type information, and it's clear where the boundary is, where SQL injection is being checked for, and what the red zone is, or the area in your code where it's assumed that that has been checked. And that will save you checking too many times, and it will certainly save you checking one time too little. So what we've been using so far has been, type information, which stops us from forgetting to do stuff, or from making omissions or switching things around. But type information can actually do more than that. If we think about the pointers, for example, within the compiler, I can add a value to a pointer. I can subtract two pointers, one pointer from another pointer, and get an int, or a size t, if you will, but it's some kind of int under the hood. I can add a size t to a pointer and get another pointer. So the compiler is keeping track of somewhat higher level logic here, because different operations on different combinations are A, either allowed or not, and B, the result of them is always correct, right? Like if I subtract one int from another int, I get an int as a result, right? But if I subtract one pointer from another pointer, I get a size t as a result, as in I get a different type than the two types that were in the operation. And we can actually use that and leverage that, and people do within the C++ standard library or Boost or other libraries. I chose the Chrono example because it's relatively easy to explain, but this could also be Boost units or many other libraries. And the idea here with Chrono is I have time durations, as in something took 5 minutes, and I have time points, as in my birthday is a time point, right? And if I say, okay, my birthday this year minus my birthday last year, that's going to be a duration of 1 year. So I can it's kind of like pointers. I can subtract one time point from another time point. I can get a duration. I can add two durations. That results in a duration. I can add a duration to a time point, at which point I get another time point. So I could say, today plus 2 years is going to be, the same day 2 years from now, right? Time point plus duration. But I can also keep track of resolution. If you look at the last two lines here, the duration casts. I could, back when when the Windows API, for example, was being developed, at least the old version, the common unit of time that you passed to sleep or to wait or timeouts or whatever in the Windows API was milliseconds. And that still works somewhat good today, but we think in much smaller units of time today. In high frequency trading, we may want a timeout that's definitely less than 1 millisecond, right? And so the general problem is that different people want different orders of magnitude, right? If I'm looking at the history of the universe, then a millisecond will be way too small, right? Like I want to maybe even measure in decades, because otherwise I would overflow my data type, right? So when we convert these to each other, we can obviously make errors, right? Like if I'm storing all of this information just in ints, history of the universe guy has his number representing decades, and he passes it to somebody counting in seconds. Well, you can forget to do that conversion, and the compiler doesn't know if everything's just an int. it doesn't know that you're making a logical error. Whereas if you encode in the type information that the one is, in units of decades, and the other is in units of minutes, or in this case, start time and end time, or the difference between them, that duration, we don't know what the units are. It's even probably dependent on the platform that we're compiling on, because it's whatever units of measure the high resolution clock has. But since it's in the type information, we can convert it into seconds or microseconds, and the compiler will call the right subroutine under the hood to do the conversion. I mean, if for example, the high resolution clock is running in microseconds, well, then the last line will be no operation. It won't need to scale it at all. But if it is running in milliseconds, well, then we'll have to multiply by 1,000. And you can do this with pretty much anything with boost units, like all of the SI units. So you can multiply speed by something and get some other value, and so on and so forth, and it will track the units correctly, so you can't make conversion errors. And this is famously went wrong with the Mars Climate Orbiter. They confused metric and imperial data types and didn't do the conversion, and so it crashed into the planet. And I would argue that the man hours lost on that project alone probably would be enough for all of rocket science to type the few more characters that they need to teach the compiler to find those errors for every project ever and in the future. So we're going to end with this taken to its logical end, and this is one of the libraries that that I authored. This is for dealing with hardware registers on microcontrollers. They're called special function registers, and to the compiler, it's just a RAM address, right? But in hardware, a special function register is actually wired to a pin or a hardware buffer or something else. And so, we have to use volatile keyword to deal with them, and people get that wrong. And we also are usually interested in a small bit field of this register, as in, I want bit 14 and 15 because, those are the received interrupt flag or sent interrupt flag for my serial port in this example. And the thing is, the user probably doesn't even need to know which bits those are and that they're part of the same register. What the user does need to know, and probably doesn't know from the normal way of doing this, where we just read named values, usually in a macro, is that the UART1 register has bits that are cleared when you read them. So if we were to read one and then the other, then the second one would probably always be clear, because the reading operation of the first one clears the register automatically. There are also other very weird things that happen in hardware, and so what we did is created a whole program which runs in the type system and checks these kinds of things. So I have to say unsafe read in that top line. It also means that we can optimize these things, because everything is still in the type system, doesn't cost you anything at runtime until we actually turn it into code. So this is a header-only library that essentially implements an optimizer for interactions with hardware registers on microcontrollers within the type system, as in fully within C++ and not part of the compiler. And this is where this ends. And there's other libraries that do these kinds of things for SQL, for example, or for parsers, for example, where you can create your own parser out of pieces, and it will track things behind the scenes. This kind of started in matrix math libraries, where you would express what operations you wanted done, and it would just save that information of what operations you wanted done in the input data and lazily evaluate it. So when you actually want that data, when you actually say, okay, give me the value at matrix position XY, then it actually calculates it. So if you don't actually want all of the matrix, or if there's some way to optimize this behind the scenes, then the library will do it in a more optimal way than you expressed yourself, based on rules that people encoded into the type system. It's called template metaprogramming. So I guess we're about to the point where we can open it up for questions, if there are any more. How would one start to introduce these concepts to an older code base? That is pretty tricky. When it comes to checked pointers, that's actually quite a good it's a common problem in older code bases. We'll put it that way. Arne Mertz, I'm not sure if anyone's familiar with his blog. He blogs about this kind of stuff regularly. That's a good source of information on that topic. The short answer is it's complicated, and it depends on your code base and how much of that you want to rewrite. But the general rule with dealing with an older code base is try and wrap the problem. So make an interface that is bulletproof, and it wraps the old interface that it wasn't. And so you may be checking the return value of the old function, which is a pointer. You check if it's null, and then you return a checked pointer to the rest of your newer code. Yeah, I mean, it's one of the toughest problems in software engineering is dealing with legacy code. So sorry, I don't have an easy answer for that. Let's see. Next question. Does your company adopt newest CPP standards on the go? Well, yes and no. We adopted C++ 11 before it was even standardized, because there is a lot there that you don't have in pre-C++ 11. I mean, for me, the term modern C++ originated with Alex Andrescu back 2001 or something with his book, but for me, sort of the modern C++ era started with C++ 11, and C++ 14. I don't think we're really using it. We are using compilers that support C++ 14, but 11 gave us pretty much everything we needed to do what we're doing now. You can do things more elegant in 14. I think some of the features in C++ 17 are very interesting. We haven't adopted 17 yet. We don't compile on compilers to support 17 at all yet. I think it is healthy. I mean, it's a matter of technical debt being dependent on an older compiler, and I think it's very important to communicate to management, how many man hours this will cost down the road, and how many expensive people. I mean, a friend of mine does consulting work and charges an arm and a leg to work on very old code bases, because young guys like myself, well, at least I still feel young. I guess I can't really call myself that anymore, but anyway, the generation that didn't grow up coding in the 80s, where this was the only way to do it, with these old code bases, they don't know a lot of the tricks that you need to do, and so these this older generation that's used to dealing with these kinds of things and can read this kind of code, they're getting more and more expensive down the road, and you're also repelling top talent, because most people don't want to work on a super outdated code base. So this is costing you in more than just man hours. It's also a recruiting problem, in my opinion. Okay, so will I be talking about Quasir in a later webinar? Well, yes. I guess I can't really answer that because at least on this platform, because we haven't even discussed it. But I will submit a talk on Quasir to the next C++ Now conference. Well, Quasir is a group of libraries. So there's what I was showing here is Quasir Bit, which is the hardware register interaction library. There's also some other infrastructure libraries like Quasir MPL, which is the fastest metaprogramming library to date, at least according to Louis Dion's benchmarks. And I will be talking about Quasir at the Code Dive conference in 6 weeks, and next week I will be talking about Quasir agent-based class design, which is another method of generic writing generic code. So infrastructure for writing generic code at CPPCon. And since that's done by Bash Films, those videos usually come out pretty quick. So that's probably the next Quasir content that you'll be able to see. But Quasir Register, if one really wants to get into the how it's implemented, that's going to be you're going to have to wait till the next C++ Now. And from a user perspective, I will be doing a 4-hour hands-on training in the training portion of the next EMBO conference, which is in March here in Germany. So I don't know if the training portion is going to come out on video, so you may have to actually come. But at the latest, C++ Now is where you'll hear a lot more about Quasir Register, or if you want training, then come to the EMBO conference. Okay, the next question was about the Guideline Support Library, the GSL. That is actually really interesting. For people that don't know what the GSL is, it's basically a best practices, a collection of best practices which you can build into the compiler. So the compiler can go through and analyze your code and tell you, oh, that's kind of dangerous what you're doing there, and here's the reason why, and here's what the experts say about it, and so on and so forth. And the GSL also has methods of wrapping pointers and so on and so forth. This is in the pointer case, you can wrap a pointer in a wrapper which has no semantic content to the type system, but does have semantic content to the GSL, as in it's implicitly convertible both ways. So it doesn't add any security as far as normal compile time errors, but it does give content to this. It's basically a tool extension to the compiler, which will then track this pointer around and actually do the checking in another tool, if you will. So because using the type system for this kind of stuff is very powerful, it's also a bit arcane and quirky. I think that the GSL is a very good solution for things like that. When it comes to things like Chrono, which is a little more complex, or even full-blown Quasir Bit, where we're doing massive things at compile time, that's out of the scope of what the GSL can do. But yeah, I really applaud the work of people working on the GSL and people implementing it into tools. I've followed Peter Summerlad's work on that, and I'm a huge fan. I'm not part of that. I'm not contributing to that yet because I don't have time. But I think that is the solution in the long run for some of this stuff. Okay, next question. Oh, the name of the blog. To be honest, I don't know the actual name of the blog, but Arne Mertz, ARNE, MER either Z or TZ. is the guy that does the blog, and he works more in enterprise software, which is where a lot of the legacy code is. But a lot of the stuff that he writes about is applicable to other domains, and he's very good at explaining things. I'm a big fan of Arna. So yeah, that's the blog name. Let's see. Next question. The limit of the CPU speed accounts anywhere modeled. To be honest, I'm not sure I understand the question. Let's just do this. I'm going to mark it as answered, and then you just repost the question, formulate it a little different, because I'm really not sure what the question is there. Okay, and there was a comment that my microphone's cool. It's actually not as cool as it looks. It's not like the full top of the line thing, but I noticed my first CPP cast episode. The sound quality on my part is pretty terrible, so I bought a good mic. Okay, let's see. Next question. Sorry I was late. Is GCC the compiler used by your company? Yes. Depends on the project. We actually have some very old microcontroller code that only works on like the microchip compiler, but that doesn't really count. It's not really relevant here. We do use GCC for the ARM Cortex microcontrollers. We also do a bit of desktop programming, in which case we actually use Visual Studio because it's been for Windows targets. They are getting better. I've lost a lot of my life to finding Visual Studio bugs, but GCC is quite good at the cross compiler to ARM Thumb for the Cortex microcontrollers is quite good, which is the reason we use it. I think we probably will switch to Clang at some point when their cross compiler to the Cortex is pretty new. It does work. I think Jackie Kay did a little bit of testing with that and told me that she didn't encounter any problems. We haven't really been testing that yet because it seems pretty new. But the advantage to the Clang compiler is that we could write some automated refactoring tools for old code. On microcontrollers, all code is old code. Like code that you see today looks very, very similar to code that would have been written when I was born. We'll put it that way. Like a lot of the code from this coding style is older than me, and a lot of it can be relatively trivially refactored into quasi-bit style. And if you want to write automated refactoring tools, Clang is definitely a compiler to do it in. It's just way easier. Somebody posted the Arne Mertz blog. I'm not sure if everyone can see that. It's arne-mertz.de. Okay, let's see. Next question. I had a great time studying Boost library but many of my peers find it overwhelming and hard to read. Have you ever used any Boost heavy meta programs in release code? What is your colleague's opinion about it? Well, yeah. This is probably quite controversial, but I think at this point, a lot of the Boost libraries are in a legacy format. The coding style in Boost evolved back when most compilers only allowed one coding style and not by any intention of the original of the compiler author. It was just they used whatever worked. And I mean, Boost, in my opinion, is amazing, and a lot of the features in the standard library came through Boost. So, shared pointer, unique pointer. Okay, unique pointer had a bit of different semantics because you didn't have move semantics in Boost yet. But the chrono library that I showed, that came through Boost. So we are all using Boost code, even though it's in the namespace of the standard library, right? The vast majority of standard library features were once Boost libraries. That being said, it is a very interesting time for Boost, because this criticism is quite interesting. I mean, one of my pet peeves is that Boost to upper basically just changes a string to uppercase. But if you compile that on a microcontroller, it may very well fill up your chip, both flash and RAM, because it pulls in so much of CLib, and it uses, I mean, it's including so many things that you don't probably need in that context, right? I mean, it's completely thread safe, so somebody can change the locale, as in which language you're using as a reference when changing letters from lowercase to uppercase, because it does depend on language. In Turkish, for example, a lowercase I will become a big I with a little dash on top of it rather than a normal big uppercase I. And Boost has implemented this in such a way that another thread could change the locale while in the middle of you doing to upper, and that will be reflected in your to upper. And yeah, I mean, I personally don't think that locale should be a singleton anyway, but that's like my dad's birth when that design decision was made. But tying this back into a critique of Boost, it's pretty impossible for me to code review that to the point where I would see that rather than looking at the assembly that was generated. And that's not bad in and of itself. I mean, I can't code review most of the standard library. I mean, even standard string is pretty uncode reviewable for a normal C++ programmer. But we know what the semantics of string are. They're very well defined for our domain, and that's hard to do, to reach that level of definition. So if you're out on the cutting edge with sort of a new and innovative library, then you have that problem of people can't code review it, and you haven't documented to the point where people don't need to code review it, and it hasn't been battle hardened. But the problem with Boost, as I see it, is libraries are accepted into Boost, and that's where the checkpoint is: do you have enough documentation? And after that, the documentation is not required to evolve. No libraries are kicked back out of Boost because they have inadequate documentation, and no libraries are kicked back out of Boost because they have an older coding style or an arcane interface. I mean, many of the Boost library interfaces are compatible with C++ pre C++11, and we can make much better interfaces post C++11. The guideline we have in our company with regard to complex template metaprogrammed code is we make a definition between user code space and library code space. And even if it's the same programmer, same project, whatever, the definition of a library is something that can be fully unit tested. Whether or not you actually fully unit test it is another question, but it can be fully user tested. Business logic can never be fully unit tested, for example, because it's continuously evolving, right? And so, no complex template metaprogramming in business logic, but yes in libraries, right? And it's also a question of, if you use it wrong, whose fault is it, right? Because it's, the young hires, people that just joined the company, you know, they're a little overwhelmed. So should they be able to just try it out? And if it breaks, is it their fault or is it someone else's fault? And you know, we shift a lot of the fault towards the library implementer, which is, you know, ties back into this webinar quite well, because you know, if you use template metaprogramming, wrap it, provide it to the user in an interface where they don't notice that it's template metaprogramming. You know, standard string has template metaprogramming in it. So if you use standard string, you have template metaprogramming in your code base. You probably don't know that because it's well hidden, right? So you know, hide it and make it, you know, hide it in the sense that the user just sees familiar language concepts and syntax, and make it bulletproof to the point where if they screw it up, it's your fault if it's breakable. And I think that's the way to use Boost in a code base at this point, because the interfaces are a little challenging. I mean, you know, C++ has gotten a lot easier to use since C++ 11. And so you may have like the Java programmer switching over to a C++ team, and they're going to have a really, really hard time with Boost. They're not going to have such a hard time with a lot of the rest of C++. So I think we need to take these very complex things out of user space and into library space, where you know, with the library, there's one or two owners and they're the only ones that need to understand it, whereas user space, usually the whole company has to potentially be able to understand the code. So that was a pretty long answer, but I hope I answered your question. Looks like I got through all the questions in the question queue.
There are no more questions. Odin, once again, thanks a lot. Okay, there is another question.
That was just a comment. Thanks so much. So, yes.
Thank you very much, and thanks for all of our attendees tonight for listening, for participating in this conversation. I hope that you guys enjoyed the presentation and you find this information really interesting and useful for you. And there will be a short questionnaire. It is actually here now on your screens. Please be so kind to answer a few questions and join us for our further events. Thanks a lot, guys, and good night.